Welcome to another episode of Code for Thought. In this episode, I'll be talking to Simon Pinches from ITER. ITER, which stands for The Way in Latin, is the largest fusion experiment comprising several countries around the globe. Simon and his team of engineers are based in Cadarache, in the south of France, which is also the site of the largest tokamak to be built. In fact, the plan was to meet Simon at the Cadarache site and get first-hand impressions on the ongoing work, but for a nasty stomach bug and severely delayed train services between Paris and Aix-en-Provence, this had to be cancelled, sadly, but I do hope for a visit in the future. Still, Simon and I had an interesting online conversation about the challenges of managing software that is created and maintained by a diverse group of contributors. And of course there is nuclear fusion itself, which has been in the press multiple times in recent years, and the hope is that the work will ultimately bear fruit not too far in the future. It seems that Simon and his team got the work cut out to help and make that happen. So here now my conversation with Simon. Hello Simon, welcome to the show. Maybe we can start by you introducing yourself quickly.
Hello, yes Peter, I'm Simon Pinches. I work at ITER, the world's largest fusion experiments at the moment here in the south of France near Cadarache. I'm a section leader within the science department where I lead the plasma modelling and analysis section. We get to do lots of lovely modelling of what we think will happen in ITER in the future and prepare for interpreting all the measurements that come out of it later in the future.
Maybe you can explain a little bit more about ITER and what it is, the organisation itself maybe, because I think there are several countries now involved, aren't there?
Yeah. So ITER is made up of a partnership of 7 members, China, India, Japan, South Korea, Russian Federation, the US and Europe. And they all work together to build ITER, this large project to try and harness controlled magnetically confined nuclear fusion as a future energy source. So ITER itself is not going to produce any electricity, but we'll show that we can get 10 times more energy out of the plasma than we put into the plasma. And then we have another mission to show not only can we do that for several hundred seconds, but also that we can do that for much longer, more like an hour, but then with a reduced energy amplification factor of only 5 rather than 10 times more.
I think we're going to talk about nuclear fusion maybe in a little while, but the organization itself is quite interesting because Cadarache is the site where the test reactor is, but the organization is, I believe, spread all over the place, isn't it? Isn't there something in Barcelona as well?
Yes, okay. So like I said, ITER comprises these 7 members, which kind of represent half of the world's population, all these countries coming together to build ITER. And each of these members have like a domestic agency which is responsible for giving things in kind to ITER. So ITER doesn't have lots of money which it gives out to all these members. These disparate countries have decided to work together. Each of them contribute things to the projects that they all agreed in advance. And so you mentioned Barcelona, that's where the European Domestic Agency is F4E, where they're headquartered and where they take responsibility for providing all the things that Europe provides towards the experiment. So bits of the vacuum vessel, coils, all sorts of bits and pieces.
So the reactor itself is still being assembled, is it? Or is it still being constructed? Or is it ready to...
Absolutely. No. We're very much still in the construction phase. In fact, unfortunately, didn't come down to visit us, but last week we've managed to put the first segment into the pit. So if you think of it like an orange in segments, there's 9 segments, and we put the first bit down into the pit. So that was the vacuum vessel with 2 of these enormous toroidal field coils on it that generate the magnetic field that runs around inside the device. So that was a big milestone that we achieved.
So when's it going to be finished?
So it should be finished. We should be ready to start doing our first experiments, sort of like the middle to the end of this decade. So there's actually a rebaselining exercise going on at the moment, since because of COVID and because many of the components that have been delivered by the ITER members are first of a kind, there's been a slight bit of a delay. We're currently assessing exactly when that will be. So the original plan was that it would start operating at the end of 2025, but I think we can expect there will be a bit of a delay on that. But before the end of this decade, definitely.
So you're a section leader of a group that looks after the modeling and the simulation and the data analysis. So let's talk a little bit about that, because obviously there's a lot of software involved, isn't there? But how big is your team?
Yeah, so here on site, I think we're something like a dozen people. A fraction of them are actual ITER staff. We have postdoctoral fellows that also join us, and we also have interns and visitors and things who also join the team. So they're not all staff. Yeah, we work closely together, each covering different aspects of the things that are required. So some people are experts at modeling the heating system, some people are experts at modeling and describing how the plasma itself organizes itself and transports particles and energy across it. And we have to bring together all these different aspects. So there are people who are experts in sort of the infrastructure and coupling things together and building what we're calling IMAS, the Integrated Modeling and Analysis Suite, which is this sort of like collective name for all the software that we're going to put together to predict, well, everything we need basically to do future physics research and also to prepare for operations in advance. But it basically boils down to having a very good predictive capability for what will happen inside the plasma, and then how to put together all these different measurements we make afterwards to work out what actually happened inside the plasma. First of all, to test how good our predictions are and to tune them so we can then better guide our research program in the future, because if we can predict what's going to happen, then we can go a lot faster. So yeah, lots and lots of different skills required, lots and lots of different physics codes that are put together, because these are essentially all physics codes. And these physics codes we're largely not writing ourselves, although some of the staff members are experts in various different aspects. They're putting together codes that have been built and developed within all the different ITER members.
That's quite interesting, because what I understand is that you have people who actually work there full-time, I guess, at ITER, and then you have the postdocs who actually come in and out in the sense that, they do their thesis and then they end their thesis and then move on to something else. So they're kind of the temporary.
Yeah. So the fellows are with us for about 2 years. There are other types of people as well. We have ITER project associates. So these are people that come from within organizations within the ITER members, and they can come to ITER and work with us for up to 4 years. And then there are also visiting researchers as they're sent by the various labs and things. So there's a whole raft of different ways of coming and working with us. We're very open. We're very happy to collaborate with people, yes. We're never going to turn down help.
I bet not. But it sounds a little bit like herding cats. If you have a mission-critical software, predict what's going to happen.
This is true. So there's definitely a balance, but we're trying to do everything sufficiently well in advance that, if through voluntary effort, and we're working closely with the research communities around the world who are already running existing tokamaks, so they have very similar software or aspects of software. If it's not possible for us to build what we need, and it's going to sort of like go towards the critical path, if you like, then we would start placing contracts in order to get this work done. But largely we can do it through collaborative efforts with teams to build everything together. Because as I say, a lot of these physics software, we're not writing. It exists already. What we're adding, if you like, is a standardization data representation to bring these things together, which hasn't happened before. And I think there's a benefit to the community as well, not just for ITER future operations, but if we put tools together that make them much easier to be applied to ITER, at the same time, we're making them easier to be applied to any machine. So there's a win-win. It's not all one way. So that there is a proper collaborative nature to this work.
Could you give it an example of one of the physics packages or physics software that you already have?
There's probably lots of different things I can think of. We have many different models for the diagnostics and also for how the core plasma transport works, as I say, to how the particles and energy leak out across the magnetic surfaces and get out, which is very important for predicting. But one of the more sophisticated things we've put together recently is what we're calling our heating and current drive workflow. So this has taken models for all the different heating systems that we foresee in ITER. So we have systems that will just heat the electrons, systems that will just heat the ions, either by bringing in electromagnetic waves which resonate with the particles, a bit like your microwave, or other models that describe our neutral beam injection system. So there we fire in very energetic neutral particles so they don't feel the magnetic field, and they collide and are ionized in the plasma and pass on their energy to all the particles in the plasma and then heat it up, and hopefully we get to the conditions that allow us to produce fusion. We get to enough energy that these particles can collide together, stick together, and create lots of energy. Also, using these systems, we can drive current inside the plasma, and this is very important for achieving our mission goals of producing a long, stable plasma that will have all the properties we like. It'll have sufficient density. It'll confine the plasma well enough that we can actually achieve this goal of getting 10 times more energy out than we put in. So as I say, we've built a workflow around lots of these different components which have been written and existing outside in the community, and brought them together in a way that we can sort of like flexibly use them within many of our other codes, and use them to describe how essentially the heat and the currents will be driven inside or appear inside the plasma. So I'd say that's one of our recent successes of integrating lots of different physics codes.
When it comes to integrating, draw a picture for us, because is it a question of having different programming languages, different environments that it runs in? What does it entail?
Okay, so the integration itself, if you like, is what this IMAS is, this integrated modeling and analysis suite. And so this has been built around an idea that originally was developed over many years within Europe. So this idea of having a common data language. So we have something called a data model, but this comprises these interface data structures for all these kind of different physics objects we have. Some of them are real objects like systems, and some of them are more abstract plasma quantities like the profiles of the different physics quantities inside the plasma. These structures we pass between the different physics codes, which, as you say, can be written in different languages. So we support many different languages. This being physics, most codes are probably written in Fortran, love it or hate it. But we also support C, C++, Java, Python, MATLAB. So there's no restrictions really on the language. And I think we'd get around it if suddenly lots of fantastic physics code started appearing in some other language. We'd find a way to also couple that in. So we have this sort of like language agnostic, device agnostic, as I say, this isn't just for ITER, data model that we can describe the data, and then it's passing these data structures between the codes, which is how the coupling is enabled. Now, sitting on top of that, you have some sort of like workflow manager that's going to orchestrate the flow of the information between all these different components. And that we've developed in a way that's not set in stone. Originally within Europe, and we adopted as well in the early days, there was a framework, a Java-based framework called Kepler, which was used with a nice graphical interface for connecting the code. Subsequently, we've moved to using Python just to describe the workflows, and now we're looking at other more sophisticated things to be able to support sort of like parallel execution distributed across our computing cluster and other computing resources using various different transport mechanisms. So it's kind of an evolving thing, but the standardization around the data model passed between components. The physics components themselves we have some software that will wrap these physics components. Given they have a standard API which consists of these standardized data structures, we can wrap them towards whatever target simulation environment we're aiming for, which I say at the moment is Python, but you could imagine we could also target some other future environment that's not yet foreseen. We've got the mechanics in place to sort of like put things together, and hopefully we're flexible enough that we can adapt to what may come up, because ITER is a very long lifetime project. Yes, I mean we don't expect to be achieving our mission goals until the middle of the next decade, 2035 or so. Lots can happen in the world of computing.
The data model is something that interests me, the standardizations. You mentioned that there's a European effort. Can you tell us a little bit more about this and where people might find that?
Yeah, so within Europe, there is something called Eurofusion, which has coordinated research amongst many different European laboratories. Within that, they started a project probably about 15 years ago now on integrated tokamak modeling. And this is where the key ideas, which we've adopted many of, came from. So this idea of having a data language, an ontology for passing information between the physics codes. So they did a lot of the groundwork for establishing this as the sort of like the paradigm, if you like. And then ITER has taken this, we've extended it. So originally, the data model was only foreseen for use between simulation codes, but we've extended it so we can actually also describe actual experimental data. So not everything has to be on the same simulation time base. You can have real data which might have different digitization frequencies for different signals. And this allows us to use exactly the same physics codes, or we can apply the same interpretive codes to simulated data as real data. So that's kind of like an extension that ITER organization has made on top of what was developed by Europe. But going back to Eurofusion, as I say, this is a consortium of many different European laboratories working together for the advancement of fusion energy within Europe.
Indeed, and they agreed on this data model, which you adopted and then extended.
Yes, they came up with the original paradigm, yes, and we've kind of like changed it, as I say, by extending it to also work for experimental data. They help us make it better, so we work closely together. They also now use this revised version, and we encourage all the ITER members to sort of like really sort of test it out for us, start adapting their experimental data into this model, because really all the developments for the data model come from people actually trying to do something new. Because as soon as you try and do something, you actually try and use it. That's when you discover all the problems with it. It's all very well hypothetically developing these things for one day in ITER we're going to do this, and like thinking we know what we're doing. But when someone actually tries to do it, you discover all sorts of problems at all sorts of levels. Even how you store the data on disk, we have quite complex structures in our data, and there's many different ways you can write it to disk for different use cases. Whether you want to read it against time or you want to read for a given time slice all the different sensors, using the data model is how we find shortcomings in it and extend it. Because we know it's not a finished piece of work. I doubt it ever will be, but hopefully it should asymptotically approach something that at least meets all our needs.
Indeed. But it reminds me a little bit of CERN, which has a similar setup. There's a staff that looks after some infrastructure, but a lot of the contributions actually come from outside and from universities and from researchers. But they also have quite a big computing cluster and hardware to back it all up, which I assume you must have as well, because I mean the data need to go somewhere. Can you tell us a little bit more about that?
We don't really have any supercomputing class capabilities. We have sort of like relatively modest, what we've called SDCC, the Scientific Data and Computing Center. So this should have the capabilities to do all sort of like the immediate processing of the data as the data is created in the machine. So to do some preliminary calculations and sort of like the first tranche of processing to be able to interpret what's seen. But detailed analysis, sort of like a turbulent simulation describing a single time slice, can be very demanding. And I don't think we ever foresee that we will do these here on the ITER site. Within the ITER members, they have their own supercomputing facilities. And so very intense, very large scale calculations will probably always be carried out within the ITER members. But we will have the facilities on site, first of all, for those who want to follow the experiments to be able to interact with the initial data. That will be set up, and it's we already have this SDCC in a initial form up and running that we use for the developing of the software now, and that will expand as ITER goes forward. Data will be streamed out of the machine, and we will immediately process that. So combining all the different aspects of various different diagnostics to have a better understanding of exactly what the density and the temperature and all the different physics parameters are inside the plasma. And this will then be also immediately streamed off-site and archived, kind of a backup, so that we can't have any kind of disaster where we lose any data. And then, of course, the members can take copies and analyze and work with that as they see fit.
I'd like to move on to something else a little bit. There is a lot of input from different members. So how do you keep it all together? How do you keep the quality of the code that gets contributed?
That's a very good question, a very difficult question to answer. Maybe practically, how do we work together? Then for that, of course, when we all started a decade or so ago, these distributed revision control systems maybe weren't quite so prevalent everywhere, or at least within the physics communities we interacted with, as they are now. So there's a big shift in that direction, and things like Git, which I think is one of the best pieces of software ever written, has certainly enabled that. That allows us to have many different teams all around the world working together really on a single version and driving it forward, combined with things like continuous integration where, we can test, if we write tests, and we try to write tests for everything, but it's an ongoing endeavor, shall we say. Yeah, some things have better coverage than others, but that's the direction we're going in. Some of the physics codes have a team behind them who are very active and really want to push it forward and help a lot in, as I say, preparing tests, running the codes, developing it, adapting it, and driving it forwards. And others, the process is a little slower and a little bit more TLC, wouldn't go as amiss to sort of like get it into a better shape. Maybe the other thing to say is a lot of our software is written by physicists, which maybe are not always the best people to be writing software. So you could imagine that at some stage, some kind of refactoring occurs. And for some of the codes which we're starting to really see that this is a piece of code which we really need to put some effort into, then we will invest in refactoring it, and hopefully at that stage we can work with the original authors because they have a vested interest in this. But this is also an ongoing conversation between the original developers. We wish to make more structural changes and organizational changes to the code. Yes. People get very attached to their codes.
Yeah, I guess so. It reminds me a little bit of my university years, because I started off as a physicist, and I was exactly in that position, that I was thrown into the deep end to write some code without actually having worked as a software engineer before and not knowing anything about best practices. So how do you actually get people gently onto the route of adopting some of the best practices? Because that must be ultimately, it helps.
I think that's a question I'm hoping you can answer. Yeah, I think this is a journey that we haven't really tackled in attempting to change the behavior of existing people. I mean, hopefully exposing them to better practices, even acknowledging that there are better practices and ways of doing things, can be a gentle carrot to pull people in the right direction. But I don't know that we have any magic solutions for how to tackle this generally.
I don't think there is a silver bullet that solves it all, because I think it's a process that needs to happen over the time. And one of the questions,
and I think it's a moving target as well, because if I think of how computing hardware is evolving, I mean, like how codes were written a long time ago. Like if I think of Monte Carlo codes, we have various Monte Carlo codes which do lots and lots of similar independent calculations many, many times to build up what the distribution of the fast energetic particles is inside the plasma. These are problems that now you can cast onto GPU type computers. And so things that were done one way in the past are now maybe perhaps better done a different way, making use of new hardware. And so there probably does come a time when we should invest in either rewriting or refactoring existing tools to take account of developments in computing hardware. Yeah,
that target is certainly moving, but I think other targets aren't really moving that much. Like, for instance, the need for testing, the need for, say, code review or some kind of quality control and measure before the code actually gets adopted into something as complex as your stuff.
Yeah, so certainly in addition to using this distributed revision control system and having all the plans for testing, hopefully eventually, the concept of having sort of like pull reviews, so reviewing code before changes are merged into sort of like the main branches, I think has been extremely useful. Even if it's just a quick review, but anyone else looking at the software that's being developed is a step forward from people who've worked on their own and no one has ever looked at their codes. Okay, some people are quite sensitive when they suddenly discover that they make a change and someone comments on it, and it doesn't always go well. But hopefully, eventually, they realize or recognize that this is actually a desire to help and make things better. It's not a criticism as a criticism. There's a joint benefit to it, and I think that's how it's taken literally all the time. So, but I think that has definitely helped. Going back to the original question about quality, maintain quality and maybe drive up quality, in the sense that we can bring in people with different expertises, more software background, software development backgrounds, software engineering backgrounds, who can look at the software and makes, even if it's just gentle suggestions about why don't you do it like this or whatever, and then over time this is picked up and the code quality, the code base slowly improves.
I guess you also have a physics background. So do you think that it should start a little bit earlier, in the sense that during the university teaching, there should be a course on software and software development, given the fact that in certain subjects, and almost all science subjects nowadays, some form of software development, at least when you go into research, is needed? Do you think we should start a little bit earlier then?
Yeah, I think it would be of great benefit to have that as a more routine option, that people could get a higher quality introduction to and education in best practices and an introduction to proper software engineering. Yeah, compared to, like yourself, I have a background in physics. During my PhD, I wrote a piece of software. This was sort of like the first time I wrote any software, and in the end it turned out okay. But this wasn't so clear. It wasn't a given. No one ever gave me any formal education on this. So it's sort of like, you learn by doing, literally. And maybe I think there are probably better ways with a bit of education before you actually embark on something to do this. Now, maybe this happens anyway, because of course, when I did it, things like Google were just, well, Google didn't exist, but AltaVista did, but that wouldn't be where I'd looked for answers. Whereas now, a quick search and you're going to find a Stack Overflow suggestion answer for any question you can come up with. And so maybe there's already a lot of exposure or a lot of information available to anyone who would be embarking on this kind of activity. If you suddenly had to write a code from scratch, I think people probably have access to much more information than ever I did at the time. But I also think some more structured introduction would be greatly beneficial, because, as you say, most physics jobs, or many physics jobs, end up involving writing some software. Even if it's my experimental colleagues, they'll want to do some analysis on the data which has never been done before, and that means reading the signals and doing something to them. I think probably everyone can benefit from some level of introduction, and perhaps some with a bit more.
There was another question that I had with regards to nuclear fusion in general. So we're going full circle back to it, because you indicated that you're trying to aim for 10 times more output than you put in terms of energy.
Correct. Yeah.
So how far away are we? I asked a similar question to a colleague of yours in the UK. So it would be interesting to get your... it's not a competition, of course, but it's a kind of...
Well, in terms of timeline, I'm pretty confident ITER is going to achieve its objectives, and I say so. It should reach its fusion power operation phase in sort of the middle of the next decade, and I think then we will really produce more energy than we put into the plasma. So that's not more energy than we put into the whole plant, just more energy than we put into the plasma. But if we're producing 10 times more from the plasma, then that still equates hopefully to a net gain overall, and from there it's just a matter of scaling it up and seeing, have there been any things that we haven't thought about before, and really making a technological and physical scientific demonstration that this is possible. So I think in terms of that should happen in the 2030s, and then you can expect, we already see in recent years a plethora of startup companies around fusion are exploring all sorts of different approaches. Once we get to the phase, and this is before anyone has demonstrated net power output, once ITER has actually categorically demonstrated that really you can win lots of energy, it is possible to get energy out this way, then I would expect it to go even faster, yes. And I would expect many of the ITER members already have their own programs in place to take advantage of this and start building so-called demonstration power plants, or demos as they're called. And I think this will only accelerate. I think the most ambitious of these are looking at being completed around the middle of this century. Some ways of thinking about that still seems like quite a long time away, but if in the scale of mankind and what this could mean for it, I think it's still a blink of an eye. So I think...
The reason I mention it is because recently, or in the last year or so, nuclear fusion came into the press, or made it into the press quite a number of times.
Absolutely, yes.
That it seems to be a little bit more realistic, or actually not a little bit more realistic, quite a lot more realistic than the initial phase.
Yes. Well, JET made its first demonstration sort of back at the end of the 90s, I think in 96. And then last year they did some more experiments that really confirmed what we all thought, but really it still needed demonstrating that the choices that we've made for ITER are the right ones, and that we're on track to make a demonstration that we will be able to win more energy out than we put in the same way that the sun does every day, which is where we get nearly all our other energy from. Well, all our other energy from.
Back to software a little bit, because assume that part, if not all of the code that you have is open source.
Oh, no. Well,
it is not?
Open in what sense? It's not... It depends who develops it. Often it's licensed to it. So essentially, it's kind of open source within the ITER members. The ITER members have decided to collaborate together and they share it with each other, but it's not necessarily truly open source. There are moves to make some aspects of it open source, but as a general rule, it's typically not. Mainly, perhaps, because universities and places where the code was originally written have not thought about it, or some of this software stretches back to the 70s. So the universities and that would view it as having made a very large investment over a large amount of time. Yeah, they haven't decided yet that they just want to give it away completely. Yeah, unfortunately, not all of it is open source. So the things that we write within the ITER organization are so-called generated intellectual property of the ITER organization. We share them with all the members, but it's not truly publicly open source. Of course, we could try and persuade them that they should make it like that, and maybe one day it will be, but right at the moment it's not. So unfortunately, you can't just log in and download a copy.
Or contribute.
No, unfortunately not, no.
Okay, so you have to be a member, or you have to belong to an institution or an organization to actually access the code, look at the code, and also contribute to it.
Yes, but I mean, the ITER members is sort of like all of the European Union, so they're quite big entities. You probably find that, like I say before, like half of the world's population would fall into one of these categories. So it's as good as open source, really. Okay. It's pretty close, yes.
Yeah, but it's not like it's a public repo on GitHub.
No,
So, okay.
No.
Well, I think that about wraps it up for today. Thank you very much, Simon.
No, thank you.
It sounds very much like you got your work cut out. With
We've got enough to do. Yes, we'll be kept busy. Yes, there's no slacking.
Well, thanks very much for the interview, and all the best for the future.
Thank you very much for having me. It's been very interesting. I pity you couldn't come to visit. Maybe in the future you can.
And as I said in the beginning, I certainly hope to pay a visit to Simon and his team in Cadarache in the near future. And with that, goodbye.